Hey, welcome back to Real World Machine Learning and Data Prep Part 2. We're going to be going over the augment and shuffle and TFRecord side of our data, training data for Birder.ai. Remember, go download Birder.ai in the Google Play Store. Okay, so in this first notebook on step 2, we're augmenting the data and we're sliding over it to write, again, CSV example files. We're pulling in librosa because it's an HPSS function. Then we're pulling in again pool for multiprocessing. And then we're setting some other data for the number of processes that we can have for that pool, our number of classes, and then here's our number of samples and number of our skip size. So we're going to be making spectrograms here. Each spectrogram is going to be 400 wide, and our W for NFFT is going to be 256. So that means the height of our spectrogram is going to be half that, 128. So our spectrograms are going to be 400 by 128. And then we're going to create a long one that we're going to be sliding over with that size. And we're going to be skipping over by 100 for each slide. EXCEX is going to be 5,000. I'll explain that one in just a minute. And then our max per file is 2 minutes. So now that we've whittled down our raw audio into Bird audio, we're going to be taking a max of 2 minutes per each of those files. These are our 3 augmentation functions. We have value, noise, and HPSS. Value is just going to randomly increase all of the values that are coming in from the audio data. So it's going to make it louder or quieter for each sample. And then noise is just going to add in random noise to that sample. And HPSS runs through the librosa effects for HPSS for the audio data. We'll be calling those in just a moment. Here is the FFT functions. This was made by Project Nayuki. This is a great project. This guy has written FFT math for multiple different languages. We used it because he has it for Python and JavaScript, as well as C, as well as many different languages out there. I really appreciate him taking the time and effort to write these functions. We grabbed it in. We're going to call the transform function here, which calls the lower ones below. Alright, so here's our augment. And our main parallel processing function. We'll skip down to the bottom here for a second. We can see that we're creating a pool of nprocs, which is 50, which is pretty much as large as we can get for memory management to go through all of these processes. And that pool calls the loop and augment function, which is right here, which at some point we'll call this slide and write. So slide and write, what this does is it takes our audio data, it performs that transform from the FFT transform above, so we have spectrograms. Then it scales each of those spectrograms by running it through an NP log, removing any invalid numbers, and then we also divide it by the mean. This is to account for any loud or quiet audio, so that way we have a fairly normal set of numbers across the board. So slide and write will create that long spectrogram, and then right here it will slide over that by in samples and in skip, and taking each one and writing it to a CSV file, as we can see right here. And important to know for the next video, actually for the next notebook, we are appending the class index onto that into that line. So in, let's say, CSV file 2.csv, and then in the first line there we would have enough numbers for one spectrogram, and the very last number is going to again be the class index, so it would be 2.csv. Yeah, it'd be the number 2, because that line is for class 2. It's pretty obvious because it's already in 2.csv, the file for it, but it makes it a lot easier later on when we are creating TFRecords for this to have that data duplicated again in the line. Okay, loop and augment. What are we doing here? We are grabbing a class index, and then we are looking for train and test, looping through twice, one for the training data and one for the test data. We're going to open up every CSV file that we have, or open up the CSV file for the class for the training data or the test data. Go through each of those lines and concatenate them into one array, which is what we're doing right here, making sure it is an int16 array, removing any invalid numbers, and then we're going to go ahead and write that to a WAV file, so we can go back and reference it, we can listen to it, make sure that is what we expect. Then we're going to convert that audio data into float32 data. We're going to do this by dividing it by the max int16 number and then setting it actually as the type float32. And here's where we get into EXC, which is really just the number of samples that we are writing, our example count. Okay, so we are opening up a CSV file to write to, and then we're going to take our audio data that we have, that we just grabbed from concatenating all those lines from the CSV file, and then we're going to send it into slide and write. So it's going to take that audio file, all that audio data, create a spectrogram from it, chop that spectrogram up into smaller pieces, and then write that to a CSV file. And then we're going to count the number of examples that we grabbed from there. We're doing that because of this next step. We're going to see if our count was better than the EXC expected count that we set from above of, I think, 5,000. And if it's still a training, if our key is for training. And if it is training data that we're still looking for and we don't have enough training data, which is all this line means right here, then we're going to take that example data again, we're going to copy it, we're going to augment it by adding some noise, and then we're going to slide and write over it again. So about the exact same data that we've now added noise to and writing it again. And again, we can do that, check if we have enough examples yet, and if it's still the training data. And if we don't have enough examples and it is the training data, then we're going to do this again by augmenting the value of it. Slide and write over that. Same check again, augmenting the value, slide and write. And then finally, if we still don't have enough data, we're going to pass it through the aug HPSS function and then slide and write over that. We're only doing this again for training data, not test data. Test data, we want it to be as close as possible to real world data, so we have a good approximation of how it's working. So we passed through all of those, and at the end of this here, we are just going to look at the file sizes that we have for each training file. We have a fairly normal distribution here, the majority of them being all about 0.75 times e to the 10. Big file sizes, but for the most part, they all have a decent amount of data to them. So we can move on to this next step, which is where we're writing TFRecords. That is step 3. So we're going to be taking this CSV data, shuffling it, and then writing it to chunk TFRecord files. By chunked TFRecord files, we're going to take all of our 1,000 classes, break them up into smaller bits, randomized bits of about 143, and then for all of the data that we have for all of those 143 classes, we're going to write to one individual TFRecord file, well, multiple individual TFRecord files that we're going to group them up so that the file size of each individual one is not too big. This makes it a lot easier on the next step when we're training a model to pre-cache that data, to sort it and filter it again, and to make sure that we are properly putting in a random normal distribution of all of our training data, and we're not focusing too much on one individual class. So this is how we're shuffling this data, and this is the main reason that we've kept it as CSV data all along. It's because we can just run the shuffle command in Linux and to shuffle that text file. Shuffle it by line. This is the quickest, easiest way that I found to shuffle it without having to pre-cache everything into memory, and it's nice and quick. So we set the number of processes here to 15. It's slower than less than the 64 cores that we have in this box, but because the amount of memory that's necessary to run this function, that's why we set it to 15 instead of 64. So, shuffling everything through, then we have CSV files coming out that are shuffled. And here we're actually making those TFRecord files. So you can see we bring in TensorFlow as TF. We have 1,001 classes. We are expecting 7,500 samples per class. That's where that 7,500 right there is. And our in classes per group is 143. So for each TFRecord file, we're going to be grabbing in 143 different classes to create them. And again, we're using 64 processes for our pool because that's what our box has here. So we're going to take our classes by making a NP array just from the number of classes, and we're going to shuffle that up. Then we're going to split those up into individual tasks, each task being about 143 in size. And then to make the TFRecords, creating this pool here and calling our make TFRecords function by class index, right? So we're sending in the length of our classes, and So for each class index we're coming in, we're grabbing all of the classes that are assigned to that task, and then splitting up from train and test, and starting. So we're grabbing all of the class files that exist for those classes. And this is again why we added the class index onto the end of the line, so that way we don't have to keep track of it here. We can just grab all of our data and put it into one big array, big list, and then iterate through it. So this next bit here, we are creating multiple TF records because we're going to use 100 times 143 for each one. So it's about 14,000 lines for each TF record, 14,000 examples. Because for each class, it's going to be getting in 100 examples. Again, we're grouping it here and sorting it, or grouping them here into little chunks, so that way it's easier on the training side whenever we're reading everything in. So we're just looping through. We're saying if we don't have a TF record, to create one, otherwise close the one that we have and then create one. TF records are fairly easy to work with. They're a little odd to get used to at first because the way that you're having to pass the data into the function below, this example proto function, which I'll show you in just a moment. So for each class file in our class files list, we'll grab a line, we'll make sure that it is a valid line, we'll grab the data from it, so all those numbers just in one list, and then we'll come down here and create a feature. And our feature is just a block of data that we're going to pass in as an example that the model will read back out later. And we have two keys in this feature. One, we have the class. That is the last number on our list here, and it's an int64 number. It's just an integer for the class range. So this is where they're a little odd, or it took me a little bit to get used to, because the syntax of TF train feature and then the property or argument of int64 list, and that is a TF train int64 list with a value of this list item right here, which is again just the last number on that row of CSV data. Then our spectrogram is a float list, which is everything but that last number on that list of CSV data. We take that example and turn it into an example, sending that feature into as an argument to TF train example, and then we write that example serialized to a string. And we do that through all of our classes into those little chunks. So at the end of this, we have TF records for all of our classes. And we can move on to the next bit, which is the actual training the model, creating and training the model. So before you watch those videos, go download Birder.ai, and then we'll keep going on. Thanks for watching.